recording this. All right, so welcome to the makeup class. For the first makeup class, there'll be another makeup class on Monday. The Monday class will be about reviewing anything we learned so far, and will also be about, now that you're almost done with the class, what else are waiting for you in the future? Given that you have this system skill, and then what are the different things that system people are doing? Some of them are cool, some of them are also really cool, but also grunt work. So, joking. Any questions so far? Now, it is, by the way, it's only like 6 of you here. So let's make this interactive and just chat away if you have anything, any questions, any comments. You guys are typically the group that responds to whatever I say anyway. So anything outside of the scope of the lecture, anything outside of the scope of the presentation, just ask. I will most likely say I don't know that, but if I know it, I'll answer. Oh, there's also multiple dudes around you watching. Okay, good. Let me know when you speak louder. So basically, you are in groups watching this. So, oh, you're home alone. Well, say hi to the computer engineering students. What we're gonna learn today is at the edge between computer science and computer engineering. Like when I was in CMU, this is a class where I see both engineering students and computer science students taking the class, actually mostly computer engineering. If you take class like digital design, or class that involve like system Verilog, building hardwares, dealing with transistors, this is one of the class that would actually benefit from those kind of knowledge. And building things like your CPU or the GPU is definitely within the concepts of computer engineering. Maybe I should check out that department sometime in the future, because I also graduated from computer engineering department. But yeah, hi. Today we'll talk about the GPU, and I believe that many of you are using them right now. If you play games, if you enjoy like Dark Souls, anyone here play Elden Ring yet? I have not, but I did play some Soul series. PTSD. Too hard. Especially for the old me to react to many of the thing that the boss threw at you. Also did not finish the Dark Soul. But yeah, so those things use a lot of the GPU to process whatever you see in the games. I've heard Sekiro is also a really good game too. Never had to. Well, I don't have the money to buy like the game when it come out. So eventually, I probably get to play them. Eventually in the next maybe 2 or 3 years when they're on like a deep discount on Steam. But yeah, those things are fun, right? And we use the GPU to play fun things, right? So today, let's look into how do we build one. A quick disclaimer, my thesis and my core research when I was a PhD is also how to build the GPU, targeting both on-chip GPU and cloud. So I did have collaborative work back in like 2011, 2012, working with AMD research on how to manage the GPU resource. Yeah, I mean, you can have a data center with the GPU, right? And then someone can actually use the GPU to do certain things. For example, you can use a distributed, it's like the technique in distributed system to train a really large machine learning model, right? Cloud gaming is another, I guess, possibility. The thing with cloud gaming is depending on what you want to run on a GPU and whether you can handle and sustain the frame rate that you are basically playing, right? Because the thing is, gaming is really interactive, right? You need to be able to put in the inputs and you should see the response almost right away, right? So let's say you play a first person shooting game, right? And you put in the input is basically shoot that guy that I see. That means that the fact that you're shooting the enemy, right? The GPU has to process that, show all the cool effects from the gun with the flare effects, with the background showing the enemy not getting shot because you're really bad at gaming, or getting shot because you're really good, right? That depends on your choice, your input, and within the next set of frames, you need to be able to render what the user need to see. So if you do this in the cloud, one of the hard problems to solve, I'm not saying this impossible, but you need to be able to communicate with the server and make sure the GPU come in and handle that and send the result back to your computer right away. That can be really hard when, let's say, 1,000 people is using that GPU. So let's say I have a GPU that's shared among like 1,000 different gamers. How can I guarantee that I would be able to satisfy every one single rendering and give the result back? So what's your monitor frame rate? What's the frame rate for your monitor? The one you're using right now? Wow, fancy, 144. So if let's say you have a 144 hertz frame rate, what does that mean? How many picture you need to be able to display in 1 second if you have a 144 hertz? Yeah, you need to draw one image every 1 over 144 the second. You need to be able to draw 144 pictures in 1 second, right? That's a pretty tall task when you have to render a really complex game graphics, right? And let's imagine 100 different people are using the GPU to play games at that time, multiply everything by 100, and then you have to basically figure out who has the earliest deadline, because if I miss the deadline, you see what? So if you cannot render 144, let's say you can only render 40, what are you gonna experience as a gamer? Frame drop, rage, salt, and if you are old like me, you are gonna throw up. Like, trust me, when you get old, I used to be able to play all kind of games. Uh, After I would say when I was like 27, age, that's the thing called age kicks in, and I'm like, wait, I was playing I think Far Cry 3 at the time, and then I'm like, I want to throw up because in this dark tunnel, I feel like my eyes cannot adapt to all the things that are changing anymore. So when you drop the frame rate, right, your eyes and your brain have to work harder. And sometimes like you just feel like you throw up and you don't want to do it in front of the computer, right? It's just bad, right? So cloud gaming is a big challenge. Is it possible? I think it's possible. You need to manage it really well, right? But things like machine learning, how many people benefit from using machine learning application these days? I mean, we all are, right? Anyone try to take a picture on your phone and it actually would classify that's a cat, that's what kind of cat is that? Let me show you if it's possible to do that. You see this? Anyone see the screen? see my output, the image of two cats. I can then click on the information down here, and it would be able to search for the cat. It would actually say, hey, the phone knows something about this. I can click on it, right? Look up the cat. And this means that they perform some classification. And it says domestic short hair, which is not. It's like a mixed breed, actually. This cat is funny. It's basically I think my cat killed the Apple classification algorithm, because every time I take a picture of him, I get different breed. It spanned from like Persian to domestic short hair to calico to like, because he is a mixed breed, right? Um, Yeah, it's also almost the same thing as when you search with picture, right? The picture you put in, there'll be some classification algorithm done on the picture to figure out what is that picture. And then it actually would analyze multiple things that are going on in the picture to know the context of what's the story behind the picture so it can do the search. There's also probably another separate algorithm to figure out, okay, are there cats in them? Are those human? What are the action? What are the action of the object in the image? And it'll try to search picture that has the same story or the context behind it, right? So this thing also can be run on a GPU, right? This thing can be run on a GPU. So now today, let's look at the overview. Now that I do a long intro, right? You probably now get that the GPU is important. So this slide is actually, I took it from the workshop I organized with TISC. We actually last year we organized a workshop with NVIDIA, and we talk about the GPU architecture, right? And then another researcher at TISC come in and talk about CUDA programming. So we're not going to talk about CUDA programming, right? We'll talk about the GPU architecture. How do we build one? What's the design, right? So let's go into that. In modern system, you buy this is older. 2080 Ti was it came out, I think, around, if I recall correctly, 2016, or maybe 17, right? It's still a really, really, really good GPU. And you buy it, you can play these games, and by the way, I play all of them. You can probably now classify me as like, I don't know, game addicts. Um, Fun fact, the reason why I go into architecture research and looking into how to build the GPU is also because I like playing games. And many other reasons, obviously, but I do like play games, right? But beyond that, beyond just playing these games, you can use the GPU to do a lot of cool things as well, like visual processing, drug discovery, DNA sequencing, trying to help people. How many of you feel like you work in computer science and you're like, what's my contribution to the human, basically to the humanity? Anyone feel that? Like you don't have contribution to humanity? Or you have like just a small contribution, you build something, you write some program. What I want to say is like, I mean, don't think about it this way. As long as you have that thought, it's good enough, right? Your cookie online are enough. But basically, yeah. So I like that. Um, as long as you have those kind of thoughts, right? Um, it means that you think about what can you do to make human go forward, right? So and using the GPU will enable you to do a lot of cool things. You can do machine learning. You can do a lot of AI applications. You can do a lot of healthcare related applications and help people, right? In a real sense. Also, you can have the GPU in the cloud as well, right? The reason why GPU is really popular these days is what they provide by having these massive parallelisms For those of you who take FunPar, are you sick of this word yet? I know some of you here taking taking FunPar right now. So you might be like, okay, parallelism again. The thing is, the reason why parallelism is nice is it's easier to do relatively in hardware. It's relatively easy to enable in hardware. So as long as you can write a program that exploit parallelisms, there's a good chance that there's a hardware for that. All right, it is easier to build a parallel processor compared to building one single processor that are extremely fast. Also easier to power as well. Otherwise, you probably need a nuclear power plant to support that single core that clocks at, I don't know, 100 gigahertz, right? It's cheaper to do things in parallel, but it's also fast to do things in parallel. So there's a concept behind parallelism and multiprocessor, right? You all know about multi-core processor, right? You all are using multi-core processor. So let me take a look at an example program. Like I can use OpenMP. Did Ajahn Kanat cover OpenMP in the fun part? Nope. Okay. So OpenMP is a framework that you can use in C++ where you can annotate the loop. This is a C-like loop, right? In fact, this is a C++, which is also C-like languages with objects. But you can run this loop in C. It would run. One thing you can do is to use OpenMP by declaring that this is OpenMP4. It's a for loop where each iteration can be run in parallel. Why? For those of you taking fun part, you would realize that B of 0 doesn't depend on B of 1. B of 1 doesn't depend on 0. There's no dependency here. I can do B of 0 along with B of 1, along with B of 2, right? I just increment everything in A by 1. It's a really simple program. So over here, there's no dependency. And this is actually a perfect program to run on GPU, right? But why? And you might be wondering, why is this good to run on the GPU? So let me go to the fundamental concept behind the GPU. I have heard that I cannot mention SIMD. Yes, no? In fun part. Last class. Okay, perfect. Yes. What does SIMD stand for? It actually stands for single instruction, multiple data. What is an instruction? Remember our x86 lecture and when we talk about the instruction? What is an instruction? It's a command in the ISA. Thank you. Yes, that's it, right? It's a command that the programmer can issue through the ISA so that the program, whatever program you're writing, it get run on your computer, right? So single instruction means that I have a single instruction like move, for example, right? I don't know, like move RCX into RAX, right? Something like this. This is an instruction. But SIMD is a little bit different from this because it has the word multiple data. The instruction we've seen so far is called SISD, single instruction, single data. It's a single instruction operated on one piece of data at a time, one element in an array at a time. SIMD allow you to do one single instruction on multiple pieces of the data. That's one of the core concepts behind the GPU. Why is this useful? Something like a vector add or vector multiply. It's just a bunch of adds, right? Add. So why don't I just do one instruction and do those entire vector. It's operation on the entire vector. It's possible, right? So the idea is, well, I use one instruction, then I apply the instruction to a multiple group of data. Over here, one add instruction can be done on 32 different data words, right? What's the requirement? It basically means that now your program has to have the parallelism, right? Your program by default has to have the parallelisms. So that's one of the fundamental concepts behind the GPU. So now let's look at the GPU core. How many people look at NVIDIA specification for their GPU? All right, so I basically just look up NVIDIA 3080 and I click on specs, right? I click on specs here and zoom this in. Oops. Zoom this in, zoom in, zoom in, zoom in. How can I zoom in here? You see this? NVIDIA CUDA core. So what is the relationship between CUDA core and the CPU core that you've seen? Anyone want to take a guess? Because I can do the same thing on the like Intel i9 processor too, right? I can go to the specification. Let's say going to one of these Core i9, right? Here, I go to Intel website and say, hey, the 16 core, right? The 16 core, 8 of them are performance core, the other 8 are efficient core. You also see here, right? CUDA core. Anyone think they are the like equivalent of the CPU core? How many people think that they are maybe the equivalent of that? Yeah, maybe, right? So it's great that you answer that. Let me see. Here. So I was looking at a different website for the 3080 Ti, right? So great question, John, you asked it. Like, does it mean that then there's 10,000 different CUDA core? Are they the same as the CPU core? No. It's one of the, I guess I can say this. This is one of the Uh, to be honest, from the academic point of view, like myself, who do a lot of research on a GPU, these are PR thing. It's not an actual core. It's not an actual core. What you want to look into that looks more like an actual core is this thing called SM, Simultaneous Multiprocessor. So this is the same GPU, 1080 Ti, I believe. Yeah. So this GeForce RTX 1080 Ti deliver a really, really high performance. This is the actual core. You have 80 core. But why does it say it has 10,240 CUDA core? These are execution units. These are the SIMD unit. So if I may, I would like to go back to the slides, right? So now let's actually zoom into the GPU core. So let's say you write a program. Most of the time when you run the program on a GPU, right? This can be a CUDA or OpenCL program. These are non-graphic applications, things like machine learning, DNA sequencing, right? But you can also have the graphic application as well. When you want to run on a GPU, you basically spawn multiple threads. These are called thread blocks. Each one of these threads is a parallel program that work on the certain, like it run the same thing. Each one of these blocks would look identical, except for they operate on different pieces of data. These are called thread block or grid. Depending on if you look at the software point of view, like software development, sometimes you use the word grid. From the hardware point of view, we call this thread block. And also each row is called a warp. And then your program will consist of multiple of these thread blocks. And then the GPU itself would have multiple cores. So again, as I said, it's a simultaneous multiprocessor or SM, right? SM, this actually stands for simultaneous multiprocessor. Is the core that actually run each of these thread blocks. So inside the core, there'll be an execution units. Anyone heard about this word before, execution units? Anyone? These are adder multipliers. Basically, the units within the core that perform an operation, like an add, a multiply, subtract, right? You basically send each thread block into the SM. And then the entire row, the warp, will be sent to the execution unit. This is your SIMD instruction. So one instruction would be work on the entire execution units inside the core. And then because you have multiple thread blocks, you just throw the thread blocks into each of this core. All right, any questions so far? Any questions so far? So the conclusion is the CUDA core is one execution unit. It's not an entire core. I don't know why they name it that way except for PR reasons. And it's actually a really, to be honest, from my perspective, right? This is bad because it's misinterpret. It allows people to misinterpret and think about the thing that NVIDIA offer as something they're not actually what it is, right? But again, a GPU core is one simultaneous multiprocessor, right? And inside the simultaneous multiprocessor, you have multiple execution units. How many people think that maybe Intel CPU also has this multiple execution unit as well? Anyone? Within the core, within the Intel core, maybe I can support SIMD as well. Yes. So if the GPU say that's 4,000 CUDA core, it means that it can handle 4,000 different parallel operations because it has 4,000 execution units. I think you got the idea now. But it does have some restriction that within those 4,000 execution units, some of those has to be in a SIMD instruction. It means that I can only issue one instruction, operate on say 30 different pieces of data, right? So it's a little bit more less restrictive. And in fact, the CPU counterpart has its own SIMD unit too, right? Because there's a SIMD-like things on the Intel processor as well. So you can run SIMD operation to some extent, right? So if you want to compare the core, I guess you look at the SM and then you look at the CUDA core. That's additional information to figure out, okay, within the same SM, how many execution units do I got, right? And when you want to compute an instruction, basically you would run one instruction at a time, which means that you execute one warp, or if you buy AMD GPU, it's called a wavefront. So warp is NVIDIA. Wavefront is AMD. They are the exact same thing. Right? It's just naming. You run one warp or one wavefront at a time, and many operations would get operated on a lot of data because of SIMD. Right? One instruction per that one lane of execution, and each box, each execution unit will have its own register file, right? So let's say I have, I don't know, 32 execution unit per SM. What's the size of my register file going to be? If I say each execution unit has to have its own register file, compared to the CPU counterparts, I will end up with so many registers, right? Because I need to support 32 of them. And each one of these execution units likely will have to support like R1 to R16 or more, right? So in this case, one of the key differences in GPU, you got a lot of register. You got a lot of register, and the register file can go to like kilobytes of data easily, right? That's actually a really normal range for the register file. But the benefit, again, parallelism, performance, as long as you have the application for it, right? As long as you have the application for it. But again, the next thing that built the GPU is, again, some instruction doesn't take one cycle, like memory instruction, for example, right? As we learned from the class yesterday, DRAM is slow. So when you need to do something with DRAM or the main memory, that can take a lot of time, right? So how do I deal with that? How do I get more performance? So we talked about SIMD already. The next thing that GPU uses is called fine-grained multithreading, right? So before we go in there, let's look at multithreading in general. This might be a new concept for many of you, but have you heard about multithreading? Have you heard about this terminology before? Or like parallel application in general? All right, so today we'll try to establish what they are, right? So multi-threading is basically the ability to run like let's say you write a parallel program. What it does is you have one application that has to do multiple things, right? You can what's multitasking in real life? What's multitasking? Do many things at the same time, right? Think of it as something similar. Multi-threading is, let's say my application has to do task A, task B, and task C. Then I would spawn a thread to handle each of these tasks, and I let them run in parallel. So there'll be a thread that handle task A, there'll be another thread that handle task B, and there'll be another thread to handle task C. And all of these threads would get run in parallel. So basically, think of thread as a program, right? But it's a subunit of the program that can be run on the CPU. So in multi-threading, each thread basically is an execution of the program can be assigned to run on one of the CPU. And there'll be more threads to run than the CPU, right? Let's say you run 10 different programs on full core. This means that each of the threads would take turn running on the CPU, right? These 10 programs can spawn also many other threads as well, right? And when this happens, there'll be a process called context switch, means that I have 4 core. I can run up to 4 threads at the time, which means I'm going to pick which thread to run at any given snapshot in time. It's as simple as that, right? It's as simple as that. Some thread would have lower priority, like I send some print job to my printer, they're gonna have low priority because I don't care, as long as eventually in the next like 3 minutes I see my I see the paper coming out, I'm good, right? Some threads are more urgent, like you're playing games and you want to make sure whatever your input got handled. So those things are important. So they have high priority. And the operating system like Linux, Windows, and Mac OS would work together with the hardware to create the policy on what what thread should be run at what time, right? So these are software multi-threading. We can also do this in hardware, and we do this a lot in hardware, in fact, right? Um, anyone heard about the term hyperthreading? This is from Intel. So Intel hyperthreading is basically running two threads in hardware at the same time with one CPU. How is that done? How is that done? I have only one physical CPU. I should be able to handle only one program at a time per core, right? But how is that done? How do I handle two threads? So this is hardware multi-threading. The idea is I'm gonna maintain multiple threads context. Thread context are things like the program counter for that thread, the register file for that thread. All right, because I need to maintain this because each program would have different value for the program counter, different value for the register file. So if I want to handle multiple threads context, I need to have a space for them. And then I would handle multiple execution in hardware. So what's the benefit of this? Because you only have one CPU. The benefit is if I have a load instruction, I have to go to DRAM. That takes a while, right? My CPU is not running anything, so I can switch and run something else. I can switch and run something else. And that technique is called simultaneous multithreading. This is done on the CPU as well. It's an old technique proposed by one of the great researchers, and it's awesome. It allows your CPU to run at a much faster rate. It utilizes the CPU better, right? So when the processor is waiting for the memory, I would switch to another thread to keep the pipeline full, basically to keep the CPU busy. It allowed the concurrent execution of useful work. So I'm going to show you the example of Intel hyperthreading, right? So let's say you have a CPU. And as I said, the CPU handle two threads at the same time, but obviously I can only run one thing at a time. So let's say I'm running thread one. And over here, I need to access DRAM, which means I'm going to have to pause for maybe like 10 nanosecond to go to DRAM, right? 10 nanosecond is at least like 30 different CPU cycle. I can definitely use that time to do something else while I'm stalling to wait for my data. So the simultaneous multithreading basically say, okay, while you're waiting, you're not doing anything, you're not running anything on the CPU, I'm gonna run thread 2. That's it. It's as simple as that. And then when thread 2 also has its own memory access, then at that point I switch back, right? So what you can see here is instead of waiting and stalling and waiting for my data, now my CPU is active, right? My CPU is active. So you get better throughput. You get more things out of your CPU, right? Are we all with me so far? Any questions so far? These are actually being done on your CPU that you buy, as long as you enable hyperthreading. Any questions? So let me ask you this question then. On the GPU, I don't only maintain thread 1 and thread 2. I maintain so many different threads. So what can I do with that? What can I do with that? The answer is actually pretty simple. I can just keep switching thread all the time to make sure the GPU is never sleep. I would run something all the time. So fine-grained multi-threading is this. about any pipeline stall. Pipeline stall is like when I have to spend like 5 cycles to do the multiply, for example. I have to wait until certain operation is done. I'm going to switch to another thread because I have so many of them, right? My GPU already have so many threads available, so I'm going to keep a bunch of those. And when I'm waiting for something, I'm going to switch to a new thread. This is called fine-grained multi-threading. So what are the downsides? When you look at single thread performance, it's going to be horrible, extremely horrible. And you also need to build extra logic to keep all the data for all the threads that you want to run. And you also have to write the program that have enough parallelisms to fill in the pipeline. This type of program typically is called embarrassingly parallel. So the program that run well on the GPU is going to be embarrassingly parallel. You can do so many things, like 10,000 different things in parallel. Awesome, run those on a GPU. If you can only do like 4 things in parallel, make sure you run those on a CPU. And the GPU execution is something like this. You have the core, right? Again, you have the warp. Warp is a collection of threads that get run together on the execution units. And each of these small boxes is a thread, right? What you run when you launch the application on a GPU over time, right? As I said, is want to remain active and run something all the time. So each snapshot in time, the core would pick one of these walls and say, run this. And it would run in a lockstep way. Basically, it means that it runs every single thread in the warp at the same time together. Run them together, right? In the next cycle, in the next snapshot in time, the GPU will say, okay, I don't know what is going to happen to warp D. I'm going to switch to warp C anyway to make sure I keep making progress while warp D is waiting, not waiting, but finishing the instruction. And we keep doing that every single cycle. Unless I have a load instruction, right? I need to go to the memory, and memory is long. So it's going to be disabled. The red means I'm not running anything. I'm waiting for my data. Because I have to wait for the data for a long time. So the GPU, what it would do to handle this slow process is it's going to basically rotate between warp B, C, and D to make sure I can still running something actively. Only if like you have multiple loads here, every single warp waiting for the data, that's when the GPU is not running anything useful. And it would wait until the data comes back, right? As you can see here, the data from warp Ds comes back, and now I have the GPU running something again, right? So that's why GPU can be really, really, really fast. As long as it has something useful to run, it's gonna keep running them, right? So what are the trade-offs? Why should you use the GPU, and why, in some cases, you might not want to use the GPU? It have a real high throughput. So your throughput, how many instructions you can do, how many different operations, like add operations you can get, is that CUDA core. So you can have 4,000 CUDA core, your throughput at the ideal case is 4,000 operations per cycle. That's really high. But if you look at single thread performance, if your program is not parallelizable, it's gonna suck for that program because it's gonna take a long time to finish. There's not a lot of complex logic to make single thread fast. So when you run a single thread program, the program that's not parallelizable on the CPU, there are so many structures built inside the chip in the CPU to make sure running these are really fast. None of those exist on a GPU. So your program performance doesn't depend on the parallelism of the application. That's why this would come up again and again and again and again and again. Because if you can write a parallel program, it's likely that you can make them fast on the GPU, even on the CPU, right? When you write a parallel program, these are really, really fast. So what application has an embarrassingly parallel uh, style of execution? I can say the graphic application. Why is graphic application embarrassingly parallel? Someone tell me that. So what are the main things you have to do when you want to draw a frame on your monitor? When you want to draw a frame on your monitor, let's say you play Elden Ring, right? And you are about to dodge a boss attack. What does the GPU have to do to figure out what should be the next frame am I drawing? Exactly, right? Thank you so much, Robert. Basically, graphics are being drawn. Many of them are using vectors, but if you think about the basic operation, these are what actually is being done, right? So if you look at graphic pipeline is a part of things like DirectX and have you heard of DirectX or graphic engines? So what they do is, well, to draw something on your monitor, to draw an object that you want to show, right? You have to do multiple things in parallel. For example, I have to first draw dots. Dots here, dots there, dots here, dots there. That will be the base for each angle of your object that you're about to draw, right? And then once you have all the dots, you would have to draw so many lines to connect them into a triangle, right? Anyone heard of the word polygon? It's kind of like a fundamental building block, right? When you want to create an object that you want to show on an animation kind of work, right? You draw triangles that when you combine all the triangle together, it becomes a polygon. It becomes the basic block of that object. Then you have a bunch of techniques on top of it uh, to smooth out the surfaces, right? You don't want like edge like thing, right? So you can also have to convert from vector as you mentioned already, like graphic are drawn in vector format, right? But then you have to convert from vector to pixel bitmap. Pixel bitmap allowing you to basically translate the vector onto an actual pixel that you want to draw on your monitor. And afterward, you want to smooth out the surface. There's so many different techniques, right? To to be applied to smooth out the surface. You then have to draw the surface, right? Then you have to determine what object to be shown on each pixel. Why is that the case? Some objects are in front of each other, right? So you need to figure out from the camera point of view what is in front. You have to compute lighting on each pixel. Everything here are the same operation, right? A lot of these are geometry and linear algebra. Drawing lines is a linear equation, right? A equals by plus c, right? I mean, okay, sorry. Y equal ax plus c plus b. Sorry, but these are linear equation. Solving a bunch of these equations, figuring out where's the dot, where's the dot, where's the dot. Does the light reflect this surface? Does the light reflect this surface? It's the same operation. It's the same operation. So there's a lot of adding and multiplying, tons and tons and tons of data, right? So now, do you see why the GPU is also really, really, really good at running graphic application? All right, so that's one of the example on why, right, this is so important, right? And to be honest, right? So how many people that know that that's also technical Oscar? You know about the Oscar award, right? That give like the award to like the best movie of the year. I'm gonna go sidetrack here because why not? You heard about the award, right? So there's also a technical Oscar that are given to uh engineering work that contributes a lot to the movie industry. We all know Pixar, right? Anyone? We all know Pixar? 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 Have you heard about this thing called Render Man? I just want to show this. What kind of fun thing to show? So it's a yeah, the lamp thing. It's a company. It's a company that do animation that are really really good at doing this. Uh, RenderMan is the graphic renderer that invented at Pixar. Uh, the actual techniques are sort of presented in SIGGRAPH. SIGGRAPH is like the best venue. It's a conference that all the best graphic paper in the world goes to, right? It's kind of like ISCA and like there's like every single area will have its own best conference that the best work of the world that year go to. SIGGRAPH is for graphics. Uh, and Renderman actually got the Oscar because of the contribution to many of the look at this. Look at the movie, like Toy Story back in the day, right? Star Wars, the prequel used them. The Lord of the Ring also used them. This is like one of the techniques that ended up being used by most, if not all, right? Animation that you saw in the movie nowadays. And whatever RenderMan is doing would run really well on a GPU as well because it also has to follow these set of stuff, right? Um, any question? I would say it's a framework and also the pipeline is I think it's the pipeline itself, right? To make sure that the image that you want to render is done quickly and in a quality that's acceptable. Like if you see the smooth surface, you don't see the weird like lightning. Um, so it's both a framework and an algorithm. So it's kind of like a mix of those two. All right. Any other questions before we take a break? So now that we are about like halfway through the makeup lecture slot, I hope you guys find this interesting, but we're gonna do a quick maybe 10 minutes break. If you have any questions, just leave us with the questions here. I'll come back and I'll get through the questions. In the meantime, I'm gonna go get some more coffee. Uh, that's kind of like my energy drink these days. I should stop doing this, otherwise I'll get. I don't think I should drink more than 6 shots a day. But yeah, if you have any questions, ask. Feel free to ask on the chat or ask when I'm back as well. I should be back in about like 5 minutes. But we'll do a 10 minutes break. We'll resume at 2:15. All right. All right. So let's resume the lecture. Right. So now I talk about SIMD, but one thing that you've learned that would break some of the concept behind SIMD are things like if else, right? If you have if else, what it really means is if I have a walk where half of them are true, the other half are false, what does it mean? When I'm running this part, how many, like, let's say each of these box are a thread, right? A single thread, and now I'm running 8 threads in parallel. So when I am in here, do something, how many threads am I running at any given time? Instead of being able to run 8 different things, I can only run 3, right? I can only run 3 different things. The other part where I'm doing something else, I can only run 5 different things, right? So this is one thing you want to be careful when you write a GPU application. This is a problem actually. It's called branch divergence. From the earlier example, you don't utilize every execution unit. And this will slow the GPU down. This thing is called branch divergence that lower the GPU performance, right? So when you write the code in GPU, try to limit if else, if you can. If not, make sure nearby threads go into the same direction. Because over here, right, if everything is true, you can run the do something and that's it. You don't have to run the else part, right? If everything is false, the same thing. You just skip to the else part. You don't have to do the if part. So these are good. But when the warp mix the thread that go into the if and the else, then that's when the GPU gets slower, right? That's when the GPU gets slower. So the actual GPU utilization, there's multiple restrictions. This is now when the dream of whatever NVIDIA tried to tell you becomes reality. That say, okay, I want to run something on a GPU. It's not that fast because, for example, every operation has to be the exact same instructions. Focus on the word exact same because we have SIMD. And if you take computer architecture already, you would notice that this means I have one decoder. We're not going to talk about it for the purpose of this class. We will expand. So basically, eventually I will try to open up the special topic on computer architecture, which basically talk about how to build CPU. We will learn what is a decoder, and you will learn that GPU only have one decoder per SM. Right? So to get the benefit of the GPU, the parallel threads, even though you have parallelism, it has to be what we call data parallel. And the command that you have to issue has to be the exact command on different pieces of data. Otherwise, GPU would run one thread at a time. It's going to be super slow. This is super slow. This is going to be a lot slower than the CPU. Right? So that's one of the problems. What else? You have to also look at the main memory as well. So I do a quick recap on the memory hierarchy, right? No, I'm not going to do a recap because we haven't covered everything yet. This recap will be on the last day of class. Right? But we can do access the cache in the CPU because we talked about this already. So I have two loads, A and B. I want to go and get my data. Let's say the green box is a cache hit and the blue box, the red box is a cache miss, right? So as we learned from yesterday, if I have a load that incur a cache hit, it'll take less time, right? Life is perfect. I spend 1 to 3 nanoseconds, I have my data, yay, right? That's the CPU. If I miss in the cache, okay, life is not as perfect. I have to go all the way to the main memory. As I said, this is like when I need a coffee beans, right? And luckily, I found a coffee bean in a nearby 7-Eleven or Family Mart. It's not likely to be an item there. I don't have to go to like Central to buy a coffee bean or like the mall or like I don't know Lotus, right? To buy a coffee bean. But if I have to, I can go to the main memory. This is like Lotus, Big C, Central, the mall, right? I am likely to be able to find my coffee beans, which is the data I want to find. But there's also the benefit in using the cache because the stall time. Stall time is the time that I'm waiting for my data. For B is a lot smaller than A. So the benefit of the cache, as we learned from yesterday, is now my data access is faster, right? Faster data access. But let's look at the CPU, right? When you handle in the CPU memory hierarchy, you have a fast L1 cache, you have multiple level of caches to make sure your data access is really fast. What is in the GPU? GPU also have the cache, right? GPU also have the cache. GPU also have the typical memory hierarchy. So let's look at what does the cache access look like in the GPU. So you can have warp A, cache hit and misses. What do you notice here? You notice that some access hit in the cache and some other access does not hit in the cache, right? So for those type of warp where some of the access doesn't hit in the cache, what can you tell about this? So how long does A have to wait? How long does A have to wait? Is it time number 1 or time number 2? Number 1 and number 2, how long do I have to wait until I can resume execution of warp A? 2, yes. So what's the purpose of the cache in this case? Because you have to stall for a long time, right? So why do I even have the cache? Anyone question this? Like why do I have the cache in the GPU? So the thing is, from the application point of view, when you program in GPU, you want to make sure these things either are green or all red, right? So that you get the best use of the cache. The second thing is it also prevents some access to DRAM. It allow you to unclock some of the queue at DRAM, because otherwise you send so many things to DRAM and everything have to stay longer because there's a longer queue inside DRAM, right? Also, when you look at the cache misses, you now have to go to the memory. At this point, you need to go to the main memory and you have to access the data, right? Now, when you look at the CPU, right, you have things coming in. Let's assume that I have 4 core. Right? One thing that I can do when I have data access is I can send the request. It's called memory request. I say, hey, I want the data for this address. And that I'll go to DRAM, right? This thing coming from different CPU core wants the data, and the DRAM would pick, okay, this request, because it's first, you get processed, I send the data back, right? And as you can see here, because I have 4 core, they all want to use DRAM. So with the limited bandwidth, like because nothing is perfect, you can have the case where one of the core sends so many requests to DRAM and clog up someone else's access. And that exactly happened when you look at on-chip GPU or even inside the GPU, because now you have so many access to DRAM, right? So the GPU would occupy a significant portion of the request buffer trying to process all this data load coming from all the SM, right? And it demands a lot of bandwidth. So that's when you look at the GPU specification, it will say, hey, I use this GDDR6 or high bandwidth memory because that's what the GPU needs. So it needs more bandwidth to satisfy all this data access coming from the GPU. So to fully use the GPU, not only you have to make sure you have parallel program where each thread looks similar, like similar looking parallel program. Things like matrix multiply, where you do multiply, like tons of multiply, followed by tons of add, followed by tons of multiply. These are perfect for the GPU, right? Parallel memory access is also okay and encouraged. Data access is going to be slower. That's also generally okay because the GPU fine-grained multithreading, as we learned earlier, would try to hide that, right? I'm not going to see the effects of the long DRAM access. But the memory access should have a better, like have good locality, like so that they can use the cache better. If they hit in the cache, they should all hit in the cache. Basically, the key message here is group the location of the access you want inside your program so that, let's say you write a program that looks like this. A of I equal A of I, B of I plus C of I, right? You want to then group that in a way that you access A0, A1, A2, A3, A4, and A5 together to make sure you use the cache effectively in the GPU. All right, so that's the second thing. Now, as a programmer, because I don't expect anyone here, or maybe you guys are crazy like me, but I don't expect people here to build your own, like propose an idea on how to modify the GPU, right? But many of you guys might be ended up using something similar to the GPU. So what else can we do to make it faster? Another thing that the GPU have is when you want to run something to the whatever ARM that share the cache between the CPU and the GPU. So great question again. So in many of the ARM processor, right? In many of ARM processor, you have the on-chip GPU. Anyone know about the on-chip GPU? So let me find a blank page again. Are you talking about like basically CPU, GPU on chip, right? Or am I misunderstanding your question? Just want to confirm. Sorry. Basically, all right. Okay, perfect. So the way on-chip GPU works is something like this, right? I have the chip. This is basically my chip. When I buy the CPU, this is what you got. What you actually got with the on-chip GPU is you have CPU 1, CPU 2, CPU 3, maybe CPU 4. Let's say you have full core, right? And then you have the GPU right here, right? And then you have the L1 for each of this CPU, L1 cache. They also have L1 for the GPU, for example, and you have the share L2. And then they all share this DRAM, right? So for the ARM architecture that you mentioned, right, one thing you can do is to allow, right, to allow the GPU to share the cache, right? They can now access L1. If it's not in L1, I can look it up in the L2. If not, I can then go to the DRAM. It's a possibility, right? I can also make sure they don't share. Depending on the hardware design. So again, great question. This depends on your hardware design. In the ARM architecture that you read, right? It's a chip built where you have the share L2 where the GPU can use. And in that case, the GPU would actually, I think my gut feeling is they're not going to share every single thing in L2 because GPU use a lot of bandwidth. So if you allow the GPU to share the entire thing, the whole L2 will be GPU's data. So what I suspect is the ARM chip say, hey, I don't want to build a separate L2 for the GPU. So I'm going to dedicate maybe a region inside this L2 where the GPU can use, and if the GPU is not using them, the CPU can also use it. Is it more clear now? You can do that. You can partition some of the L2 for certain things. And you might be asking how, right? There's a technique called wave partitioning. From the lecture yesterday, you might be remembering that this set associative cache where you can have the 8-way cache, right? This means that I have 8 cache block per set. I can then say the GPU can insert 2 cache block And then the rest of the 6 cache blocks are coming from the CPU. So in that case, you partition a quarter of the cache for the GPU. All right, so this is basically one thing that architect can do. Why is there a share L2 for the cost? Yes, for cost saving. Because if I have to separate L2 for each of the CPU, that's gonna cost a lot. So typically, when you go to L2, they are share. The second thing is some application are parallel application, which actually have shared data. So this would allow you to basically keep one copy of the data in the L2 instead of having multiple copy of that same data in the private L2. But again, these are hardware design. I can change it if I do some evaluation in the future and think that, hey, private L2 make more sense because it gives better performance, right? So these things, from my point of view of a computer architect, is never a static thing. It's never static. It's just basically right now, these assumptions make sense for the application you run. And I can change it. This is one thing I always really want the students who take class in computer architecture, including computer science and computer engineering, to think this way. Because at the end of the day, you are programmers and engineer, right? You can change your software for sure, but you can also propose new hardware. As I said, hardware is never a fixed thing. We change it all the time by Intel, by AMD, by NVIDIA, right? This is what I do for a living, right? I change the hardware. So keep in mind that these things are never static. And if you feel like, okay, this thing doing X and Y and Z makes sense, if you can change this part in the hardware, do it. If it makes sense, actually, it will be a positive thing and everyone would like the idea, right? Okay, so is it more clear now? All right. So what else can we do, right? So I'm gonna quickly talk about this. Is actually one of my thesis work. I propose how to one way to implement virtual memory on a GPU. So this is traditional virtual memory on a GPU that was kind of assumed about, right? But with this, there are quite a number of problems. I'm gonna talk about this high-level overview because we are not talking about virtual memory yet. That's a topic for next week. Sorry about that. But with this GPU assumption, you have multiple problems. You have basically limited space. This is the cache for virtual memory. You have limited amount of cache. And every time you have to change from virtual address to an actual location in DRAM, that takes a long time. Then there's a lot of cost when you have to copy the data from the CPU memory to the GPU memory. So moving the data between the CPU and GPU is a big problem. I do have a thesis and two papers on how to build this. We actually got a comment from and people from NVIDIA research that actually what I propose is like something similar to what they've done to the GPU. So the newer version of the GPU that comes out now have virtual memory, so they have a better support for cloud. You also need to cover the case where right now the GPU is controlled, right, by the CPU. The CPU is the host and the GPU is the device. The CPU would run the application and say, oh, okay, that's a GPU application. I'm going to throw it over to the GPU. I will send the data over and I'll tell you when to start running this. The GPU basically takes the command and execute the code, right? So this is basically what happened. The CPU has its own memory. The GPU also has its own memory. And the memory on a GPU, as I said, has higher bandwidth, right? More banks, more channel. These DRAM are connected. So if you buy a GPU for your desktop, it's going to be using PCIe. If you data like if you are running a high performance computing server, it can be used in NVLink. There's a much higher bandwidth and a lot faster than PCIe, right? But again, these are a lot slower than the link between the cache and DRAM, right? So when you do this, the requirement when you want to run something on a GPU is this. You must transfer the data to the GPU before the GPU start running. Basically, if you need to run something, make sure the data is there. Then when you finish running, you need to transfer the data back because they share the data, right? But you need to manually transfer the data back and forth and back and forth. To get the performance, as I said, this data transfer takes a long time. So you want to minimize this. And a typical operation is, as I said, the CPU and GPU has its own memory, right? So you first call CUDA malloc. This is your old friend malloc, but instead of malloc on the CPU, when you call CUDA malloc, you allocate the memory on the GPU. All right. The only difference is, yes. So now you can have all the segfault, but on the GPU side, right? Fun. So could you run CUDA malloc, allocate the space on the GPU. Then when the data is ready, right, you transfer the data back. No, sorry. When the data is ready to be transferred, you transfer the data from the CPU to the GPU. Sorry, what is the animation here, right? So you transfer the data over. Another point of bugs that can happen beyond just malloc and segfault. Don't forget to transfer the data. Oh, it's not bad. A4 is not bad. I think it's easier. I don't know. Maybe that's why I only assigned 10 days. I'm sorry if it's actually harder. Um, then when the data is ready to be transferred back, right, you launch the kernel to process the data, and you can transfer the data back to the CPU when you finish. You also can do what we call unified virtual memory. This is like one of the technology enabled by NVIDIA, right? So the idea is I can create the illusion that the two memory are the same thing within the same address space, and you can call CUDA malloc manage, where you can enjoy segfault but without worrying about the data transfer, right? This is easier. It basically allow you to kind of treat the pointer as if they can either be on the CPU or the GPU. And then the CUDA driver would manage the rest, right? So the data movement is automatic. But again, the benefit on paper, this is really good. It makes the GPU simpler to program. You only have to worry about things like segfault and not the data transfer, right? But the problem is now performance is a problem. You cannot predict when to move the data in. It doesn't work when multiple applications want to share the GPU, right? It can also lead to lower performance. So it is still like making this work is still an active area of research. So the last thing to get the most use out of the GPU is you also want to make sure you limit the data movement between the CPU and the GPU. All right. So sorry about forget to change the date here. July, what day is today? 6th, 2022. I guess you can now see when did I give this talk. And any question about GPU? That's it for today. I want to tell you about some of the cool things I've been looking at. Because otherwise we'll meet each other on Thursday. I'll be here for maybe 10 more minutes to see if you have any questions. Thank you so much for joining us, and I am going to post the video after this video finish rendering.